Sensitivity analyses can be used to better understand the dynamics of existing numerical models. The method can be particularly useful when applied to grand challenge problems that exist in biomedicine. This past summer, I worked with my research lab to research how we can use sensitivity analyses to analyze models that describe kidney transplant patient dynamics. So, what exactly is a sensitivity analysis? Sensitivity analyses show us how changing certain parameters affect the dynamics of a numerical model or simulation. For example, if we change initial condition values in a model, we would want to find out how the different aspects of the model, such as states of interest, would be affected. A sensitivity analysis can be defined formally by the following differential equation. In the equation above, we define f to be the differential equation with variables t, which represents time, y, which represents the set of states in the model, and q, which represents the set of parameters of interest we want to investigate. If we want to define a sensitivity with respect to a certain parameter, that is, how sensitive the model is to changes in the parameter, then we would calculate it with the following partial differential equation. We can apply this mathematical concept using computational tools like MATLAB so we can solve problems in biomedicine. For my particular project, I conducted a sensitivity analysis on an existing renal transplant patient model. To tell you a little bit about the model, its goal is to find the optimal amount of immunosuppression for a transplant patient. Massachusetts General Hospital reached out to my research advisor a few years ago with the issue of how to optimize drugs that suppress a kidney transplant's immune system. If suppressed too much, a patient can be susceptible to viruses, but if suppressed too little, a person can be susceptible to their own immune system, rejecting the transplant. My project in particular strives to answer the following questions. How does changing the initial conditions of the model affect the model as a whole? And what are real-world implications of these results? We consider the following 6 states of interest in my model. First, we have HS, which is the susceptible nephron concentration. That is, the nephrons that are susceptible to being affected by the BK virus. Nephrons are the basic unit of measurement of kidney tissue. Next, we have H sub I, which is the infected nephron concentration. That is, these nephrons have already been infected by the BK virus. V defines the BK viral load. EK defines the immune system response to the allograft or transplanted kidney. E sub V defines the immune system response to the BK virus in the patient. And C defines the amount of creatinine in a patient's bloodstream. If found at high levels in the bloodstream, this indicates that a patient's kidney function has been impaired. The parameters of interest for this sensitivity analysis are the initial conditions on the states. We want to see how the model as a whole will be affected by altering the initial conditions of the previously mentioned quantities. The complex step method is a novel research method developed by my research advisor, which calls for using complex numbers, which have both real and imaginary components. For a function g that takes parameters t and q, we can approximate the partial derivative of g with respect to q by taking the imaginary component of the enclosed component and dividing it by a pre-selected step size h. After understanding these aspects of the model, I was tasked with developing a numerical simulation in MATLAB that would carry out the complex step method and graph the sensitivities with respect to initial conditions. At a high level, this was the process I followed to implement the complex step methods to approximate sensitivities. I first defined the kidney transplant model as a differential equation system. Then I defined a step size for approximating the differential equations, which for our purposes are the sensitivities. Then I set up an ODE solver in MATLAB, specifying the option to solve with complex numbers. Next, I saved the output vectors of the ODE solver, which we can plot to show how the model will be affected over time. One major challenge I ran into was an issue with the interpolation method deval. It failed to work with the complex numbers that we were using in my program. As a result, I decided to perform a study to examine if the MATLAB function interp1 would be a viable alternative. First, I analyzed the difference in the output of both deval and interp1 using this differential system, dx dt equals cosine of t, which is along the real number system and not the complex system. I found that the results were quite comparable and only differed on the order of 10 to the negative fifth. Next, I performed a study on the logistic equation. I implemented the complex stat method, using interp1 to perform a sensitivity analysis. In this analysis, my parameters of interest were the carrying capacity, growth rate, and initial population. I concluded that interp1 was a viable alternative, and I substituted the function into my MATLAB script. Finally, after many iterations of my script, fixing bugs, and formatting the output plots over a series of weeks, I arrived at the following plots, which I think are quite beautiful and explanatory in the context of our problem. The following panel of plots depicts the sensitivities with respect to the initial condition HS0. If you'll recall, HS0 is the initial amount of susceptible cells. Over time, you can see how sensitive the model is to change. By extension, we can see how sensitive each of the states are to change. In terms of real-world implication, let us take the first panel in the second row. Intuitively, it makes sense that the sensitivity of the virus or the viral load would increase and subsequently decrease in an inverse relationship to the level of susceptible cells, as the virus proliferates upon contact with susceptible cells. Similarly, we can view the plots with respect to the parameter HI0, which is the initial amount of infected kidney cells. Next, we can see the output plots with respect to V0, the initial viral load. And then next, we can see the output plots with respect to EV0, the initial immune system response to the virus. And then here are the output plots with respect to EK0, the initial immune system response to the transplanted kidney. And finally, here are the output plots with respect to C0, the initial creatinine concentration. All in all, I was able to successfully complete my sensitivity analysis for all 6 parameters of interest. My project will most positively benefit the work of my collaborators, allowing them to improve their existing patient dynamics model. In the long run, my research could help recommend to physicians the optimal immunosuppression doses for kidney transplant patients.